Okay, so welcome. I go through a recapitulation of second part of last time, so from the recurrent neural networks to the word embedding. That is how we treat the input to these kind of networks when we want to do, let's say, when we use as input sequences of symbols, for example, language. Then the encoder-decoder architecture in general, and then I will move on with the attention mechanism that leads to transformers, that is the foundation of the large language models. And then, not necessarily today, but I will close the architecture kind of overview with the graph networks and autoencoders before I go to kind of list of or presentation of different application of the architectures that I have been presenting so far in material science and chemistry. So the recurrent networks are implementation of say models that accept inputs at different times. So the most simple would be the so-called finite response system, where an output of the model depends on input at a given time step and previous specified number of time steps. And from the point of view of a neural network, this means that say the network, that here would be just a square, would accept inputs from an input at times t and t minus 1, t minus 2 in these graphics, and give an output. Then the same network would accept an input that is shifted and give another output, right? So the square is a full network, possibly fully connected. And what we actually learn is the weights. So the model is specified by the weights for all the layers that connect the neurons, and so give the transformation from the input to the output. So the simple implementation has a finite number of input steps. So we just predefine the size of the input and say, okay, input has a certain size, could be a vector of length n, and then we just kind of attach together three inputs and give it to the network, and then the next steps it will be another three inputs, and so on and so forth. A bit more significantly more complex is the idea that to get rid of this established number or prefixed number of previous steps that give information for the learning of for the prediction of the new step, we just say, okay, we want the model that is a function of the input at that time and the previous output, right? So this is the general setup of a time series. Could be stock market prediction or meteorology, in which you say, okay, I have some readings at the moment, and I want to predict what comes next, and we give as input the readings and the output at the previous step. And this should be very familiar to, say, kind of condensed matter simulation setup, where we have say information that could be position and velocities of a particle. That would be, say, the output. And then we give it as an input to the next step, where at each step we may change whatever external, so temperature, or there is an external force that is modulated in time, and so on and so forth, and we would predict the outcome. So interestingly, if you set up a problem like this one, we actually know the model, or at least we know the differential equations that govern the evolution of the system, and we want to integrate them, right? So we have molecular dynamics to do that, or we can just train a network to do the same, and depending on the situations, either can be better. Now, from this, so and this here would be the kind of a graphical implementation of these infinite response systems, in which we say, okay, this is the square is still our network, and then it accepts input from the current step, and the other part of the input is the output from the previous step. Important thing is, again, the network is always the same. So when we train a network with a certain given weights, and it will react to these inputs, that is combination of input and output of the previous step. More generally, people set up the state system model, in which we kind of decouple the information that the network or the model transmits to the next step. So typically with the letter H. So this is decoupled from the actual output, right? So we have a state as an input from the previous step, and the input at that step, and the output would be new state and the desired output. And this, again, thinking at atomic molecular system, you could say that what you propagate is position and velocities, but then you're interested in some other observable, some distance of some bond, some angle, or some other observable. This is actually what you output, and maybe this is what you, not maybe, and this is what you train the network on. So you may not have for training the information of velocities and position at each time step, but you may have some other reading from some experiments, for example, and then you say, okay, whatever is the inner input, I predict the output. Of course, if you don't give information in the architecture of the network that the state should be position and velocities, the network is free to create its own inner state that doesn't need to be as simple to be understood as position and velocities. But nonetheless, the analogy remains. So we have a state that is propagated and output and input at that particular time step. The network is always a deep network, specified number of layers. The only prescription is that you get an output and a propagated state that here, for simplicity, is taken out, like the arrow goes only to the last layer, but it could be any function of all the layers. There is no limit to that. And to be kind of a bit more specific here, at the end of the day, what one does when designing this network is specifically to design how the state function is extracted from the network, and how the input is, say, concatenated or in any way combined with the state. Right here, I just put x plus with a circle, so some kind of concatenation with the state as an input, but it could be any other operation, like a scalar product, whatever. So this is like the knobs that we have to control the network. Otherwise, especially if you use a library for training the network, all the rest is specified by the size of the network, right? So you just say, okay, it's a certain number of hidden layers and so on and so forth, but I'm addressing a special infinite response system, something I want to train a recurrent network on, and I will design exactly how I want to extract the information. Of course, there are a wide variety of predefined class of recurrent networks, but in principle, one can play at will with this kind of architectures. So what I didn't show last time is the kind of general scenario of this recurrent network in terms of input and output behavior. So the cartoon here would be the simple network that is not a recurrent one. So you have an input of specified size, a network, and that makes a prediction on an output, right? So this could be any multi-layer perceptron that makes any kind of prediction, classification, or regression. Could be a convolutional network. The thing is that also for an image recognition network, we give an image, not typically, but for a traditional convolutional network, the image has a specific size, and then we get a classification, what it contains, or some other reading out of the image that we may be interested in. The recurrent networks then have this kind of possibilities. You have a single input and many outputs, so that you need that you construct a network that gives out an output in a sequence, but you give only a single input. So the typical case here would be, say, image captioning. So you give an image as input, and you want to get a description of the image, not just a classification. So what it contains, it could be natural language, or in any case, a list of objects that are contained. Then you have the many-to-one. This could be that you input. So in general, here you input a sequence, and you want to just give to get a single output, a classification. So this could be a sentence classification. For example, so you have a natural language text, and you want to just classify whether that is sad or happy content, or inappropriate content, or whatever. It may not depend on a specific word, so it has to analyze the whole thing as a sequence.
Question about that image captioning.
Yes.
How would the how can I say, the first column influence the next column? So in the hidden layer for captioning. So yeah, I can't really imagine how that would work. So the left hidden layer would somehow, okay, there's an object, and then influence.
Yeah. Okay. Maybe. I wanted to tell it later today, but I can do it now. So in general, this the network for this kind of language task. So this is our network. Will output say a probability vector, right? So it will say, okay, at this point, I have a certain probability to have the word hi, the word you, and so on and so forth over all your dictionary.
So it's kind of a correlation or what?
Exactly.
The
So
detection of the object in the image is correlated with the other object. So
exactly. So in the training, you give images with captions.
Mm-hmm.
The point is that you cannot train a typical convolutional or any other kind of network, because the length of the sentence is unspecified, and also the kind of shape. You cannot even say, okay, it will be subject, verb, and object, so that you can kind of hard code that the different length can be taken care of. So it could be anything, and then you have a probability assigned to each output, and then the next step uses again the image or some kind of information that has been processed at the image and the previous output, because of course after I there can be only something and not something else. Or maybe I expand here because
I just wonder what that means in the image.
No, that's a very good point. I wanted to specify later, but it's the right time, essentially. So you have at the end a probability of y1, and in the next step, now I am, okay, let's do in this direction. Now I have again the network. that has well, we use this H because so H is knows about the output, right? It's not explicitly the output that goes into the next step, but it's again, so we have the image. If you want still the image or just this H, it doesn't really matter. The important thing is that again I get a probability. But now the probability is y1, y2 given y1, right? So that information is in the H, and so on and so forth. And in practice, these kind of models build a tree, kind of. So you have so possible outputs. Again, this could be I, U, and whatever. And then for each of them, there is a possible continuation. And what it is done typically is to say, okay, I select the outputs from the previous step that are most probable, and I consider only that those from the next step. This is called a beam search. So you could imagine that you could put every possible sentence of every possible length in such a tree, and you don't want to analyze the whole tree. You just say, okay, I keep the most promising from the previous step, and then I analyze how the sentence could continue. And this is what is called beam search. This is what it is typically done. Even in modern language models, I would say, not much better than that. Okay, then, the sentence classification is, okay, not so complicated, right? So you give now the encoding of the sentence, and then you make a single classification. The many-to-many, okay, that's what I started discussing last time. So it's the general sequence to sequence, kind of the broader class. You can think of translation. So you give an input sentence, translation, and you get the translation in another language or summary or whatever out of that sentence. And here again we have the same thing, that each output depends on the previous output, and typically the last, so the input that triggers an output is called start of sentence. You'll find it sometimes. And the last output is called end of sentence. So when the model thinks that that's finished. And then you have the special case of synchronized many-to-many, in which you basically have an output for each input. But the input implicitly has a sequence, and just to fix the ideas, this would be, say, movie captioning. In which you want to describe what happens in could be every single frame or a group of frames in the movie, and the description depends on the instantaneous image and the previous image, right? Because if something is moving, you want to capture the fact that that thing has been moving. Then again, all this has had a lot of motivation and application outside science, so the image could be anything, but they are coming, so this kind of models, they are coming also for scientific application. So already many groups try to have a microscopic image kind of captioning or description, or even a movie. So if you have a dynamic kind of microscopic image, you want to keep track if some dislocation moves or something like that, and then you need to resort to this kind of you need one possibility is to use this kind of networks. I will try to find some examples for the next lecture. Okay, then again, as part of recapitulation, I'm now focusing a little bit more specifically on the sequence to sequence. That is a broader case. So here I had last time the recurrent network would accept as an input sentences in one language, for example, and give as output the translation that here I put it in Italian. The features here are that you don't have a one-to-one correspondence between the input and the output, meaning that specifically the subject I is not translated in correct Italian in this particular sentence. The information is encoded in the verb. Ho mangiato is ate, or I ate, but there is no explicit I in this. It's just kind of implicit in the way the verb appears. And then in English you have the modifier of the pronoun when you have a vowel next. This doesn't. Okay, there are different rules in Italian. One important thing here is that you have the kind of female gender for the fruit apple, mela, and you have to how to say, tune the pronoun, so the article also in the female gender that doesn't exist in English. So you have different features, and so that means this particular part of the output may depend more on this input and so forth and so forth and so on. But the general idea is that we give all the information, we generate a state vector, and this state vector generates the output. This is the general layout of this kind of time series models. And as I mentioned last time, the first decision to be made is how to represent words. And here I want to make also a specification that this becomes token in 1 second. So the general idea is that we start, as in many cases for machine learning models, where we have input that is not naturally a numerical kind of representation, so that you have an observable on a scale, or if you have an image, you would say, okay, I have a matrix of intensities, or 3 color intensities, and so on. We have the so-called one-hot encoding. That is just the most general thing we can think of. We need to define a dictionary, so we accept all these possible inputs, and then we set a vector that has the same size of the dictionary as of D, and the first item is 1000, the second is 0100. And as naive as this looks like, this has been the basis of many successful models, not only language, I mean very, very loudly for languages, but also for chemical representation. Because what happens at some point is that we embed this representation that has the feature, I would say positive feature, that every item, every possible object is equally distant to all other objects, right? So if you evaluate the Euclidean distance between any pair of data points, it will be always the same. And this, we can think it as a good feature, because we want the model itself to learn the distances in the most proficient way to perform its task, rather than just saying, okay, now I have all the whatever pronouns in a subspace, and then all the verbs in another subspace. Could be, and actually people have been doing these things, but then we at some point we thought, okay, let's outsource this task to the network itself. So we just say we have the one-hot encoding, and then there is an embedding matrix that goes from the hugely dimensional one-hot encoding to a lower dimensional representation that, given the training, so this P matrix would be projection matrix would be of some dimension, and project the one-hot into this word embedding, and this all the coefficients of this matrix are learnable parameters for our network. So we have to think this input here already as some kind of network that goes from the one-hot encoding to the actual input of the network that we want to learn. Or we can put these two together and say, okay, something learns the representation and then gives it to the recurrent part of the network that does the task. Should keep in mind that any time you see this kind of graphical representations, we could always have a fully connected multi-layer perceptron that does the whole task. All this reasoning as the task to lower the complexity of this possible multi-layer perceptron, because we want to start saying, okay, we want to decouple the task. I go from the one-hot encoding to some kind of representation, and this representation in the input of another network that is actually the recurrent network. If I put everything together, I end up with the order of magnitudes more parameters that I would need to learn. Some of them would be naturally zero, but without telling that the learning algorithm has to kind of find out or mimic this kind of thing. Okay, so some leftover should not be here. And then, okay, so the word embedding, what I wrote but I didn't comment. In practice, we are not fixed to have one-to-one correspondence between this one-hot embedding and words in the language, but we can have any combination or part of words, right? So because especially if we want to capture that this N, for example, is actually A with a possible modifier, we need to split this word into two tokens. So token is the general word to say in a language model kind of scenario, what is the atomic unit. So we don't go smaller than the token. So the model doesn't know anything below the token, unless explicitly said. And trial and error, if people tried with just letters, of course they have a few letters, but then you have the other embedding that it is a nightmare. So there is a combination. And some, today I will also go through a little bit of the numbers. How big are these representations? Now, this architecture that I sketched has, so this architecture meaning this one, it's pretty general for this kind of sequence to sequence, but has two major problems, or well, three, I would say. So one is that we have a first part of the network, this is actually called the encoder, that would treat the input, the actual input, and then at some point you have the trigger to give the output, start of sentence. And so whatever the network knows at this point to start the decoding part is embedded in this vector. So you have to, so this state vector hn, so it can have any dimension as we like. So we have to construct the actual network here so that you get a certain output state. at each step, and then we kind of freeze the output as the encoding of the sentence. So this is really a vector with a certain number of dimension, numerical vector, and this should contain, in principle, all the information we need from the input sentence to make the translation, right? So somewhere in this representation it has to know the sequence of the words, which words are used, which modifier are applied to the words in order to get the right decoding. But the way such a network would work, you give this embedding of the or representation of the input sequence, and then it goes to the first part, and then there is a new state that depends on this embedded encoding, but also on the outputs of during the decoding. So basically, the information, this HN, will get diluted by the new output coming out from the network. So this could be an issue for long sentences, and that before the end, the information is a little bit lost. Then the other problem is that also the decoding will lose memory of this initial state. Okay, no, the other way around, sorry. This is what I said now. The other problem was the first problem, actually, that the encoding itself could lose memory of the beginning of the sentence, because this is strictly sequential, right? So it goes step by step. So each step modifies the encoding until the final encoding. And so what happens at the beginning of the sentence might be hardly represented in the encoding. And then we have the problem that I just said. And related problem to the fact that we are diluting the information when we go on into the translation, so the output sequence, is that different part of the output sequence may depend on different part of the input sequence, right? So here loosely the order is similar, the verbal part and the object part, but there could be very many cases in which order is much more scrambled in the translation. I mean, generalized translation, just not keep your mind fixed to language to language. Natural language to natural language could be that we are captioning a sequence, and then we want to have different kind of importance that we give to different part of the inputs when we want to look into the translation. So this is where I closed last time, that we say, okay, now instead of having a sequence, so a state that depends sequentially on the previous input, we now invent a new function of the input that is called the context. And this is very, I mean, its terminology is kind of what we use also for transformers. So we have this context variable that it is, say, instead of having as the final output the last state, so this is again our encoder, so I encode the words and then I evolve the state function, but the final, so this, instead of using only the final state, I keep track, keep in memory of the previous states in the previous steps, and then let's say, more simple, where I closed last time, I take an average. So I say that I define the variable context, that is the average of the state functions in all the previous steps. So in this way I equally weight all the state function inside the, so kind of I have the center of mass of all the representation that in this sense has better information about the overall sequence. And then the next the easy generalization step, instead of having a simple average, we have a weighted average. So we just say, instead of summing 1 over n's, we sum weights with the constraint that the sum of the weights is 1, and each weight is bigger than 0. So we have really like a probability distribution of the outputs, and then we weight them. So in this way, we would have the context as a weighted average of the state function over all the encoding, and we have to construct this kind of weighted average where, so these weights here are learnable parameters, right? So if we go back to this thing here, instead of passing hn, they say that in our decoder we pass some kind of linear transformation of all the state functions, and this is given as an input to the decoder that arguably has more interesting information for the decoder than just taking the last state function. And then you may say, okay, but very probably different steps that are function of the previous outputs may need a different context, so may need a different linear combination of the output, because then you start pointing at the words that are more important. So the most important for mangiato is 8, because this is the past tense of to eat, also in Italian. But also you have to have the context of what happened around, because I have to put the right ending. So maximum attention is here, but all the rest of the senses is also important. And I used already the word attention, because now we are moving towards attention mechanism. That is exactly what did kind of the revolution that made all this sequence to sequence possible. And okay, so the idea is that first of all we have maybe I just copy this one that I just. So if we stay with a single kind of context idea, so there is only one context variable that is learned, so actually the weights are learned in order to construct this context. What we do is to say, okay, we have let's say the weights should be a function of the okay, I need another graph. Okay, 1 second. Let me just sketch to put the symbols here. So I have the decoder part, so the encoder part and the decoder part. And here there is something like H1, H2, Hn, and then now I have a change variable just to make it a bit more. So it would be state S1, S2 when I'm in the decoder part. And so I want to construct this context, and I need to have weights that are function of state H and state at the previous, so would have the I and I minus 1. Oh no, I need two variables. So this would be like t. So here I have a variable t that evolves and a variable I that evolves. And the weights is the weight related to the specific value of the state, right? So we want the weight that connects the state function in the encoder, and this is related also to the value in the decoder. Let me repeat here, encoder, decoder. And to do that, so the weights again, we need that these weights sum to 1, and the weights are bigger than 0 or equal to 0. So to do that, in practice, we just define a function that connects this thing. So example of this function could be scalar product. And or a full linear transformation. So I just learn a W if here I use just the letter G, that makes the kind of generalized scalar product. So I have a matrix, so S can have any dimension, H can have any dimension, and I just have a learnable. So the catch in all these stories that we dump all these linear transformations in the game, and whenever you have, I try to be consistent with this W ladder, you have a matrix of weights that we learn. And the next step is, after I just learned or made this mapping, I have to transform these E variables into actual weights. So we use the usual trick of the softmax. So basically we say, if I take the exponential of the AI and I divide by the sum of these exponentials, I get something that it is, each W is positive, and they sum to 1. So this gives us so now the output Si would now be a function of the input at that time, or maybe I use T to say when you are in the encoder, and this context variable. So again, the context is this one, right? So we have input sequence, we have a set of weights, and we calculate the context, and this is passed to the model that is calculating the output using the input at that particular time step and this context variable. So the context, again, this is the crucial part, is some kind of learned weighted average of the state function after giving the input, right? So instead of just focusing on the final one, we keep track of all the state function that keep track. So each of them has memory of what has happened previously, but now we take an average, a weighted average of that in order to get to the output. So at this point we have a mechanism, so a learnable mechanism that gives us how the state propagates in the decoder. Just keep in mind that at each step you would have also an output, right? So the output depends on the state at that particular point in the sequence, so time step, and the output. And the input coming from that. Now, the generalization of this context kind of architecture is the, now we go from context to the key value query architecture. So this is Q. Oh, okay, yeah, normally it's, okay, so the query is before. Okay. Query, key value. So we have this idea. Let me just sketch the architecture and then I comment on it. Okay, so for each state of the system, I now define some other vectors called key value and query vector that is related to the state of the decoder. So these vectors K, V, and Q are projection of this state vector that kind of attend to different contexts that are in the input. So in the state. So imagine this in this way. So if you have a sentence, you need say some grammatical context, so you need to keep track if certain word is a verb or if it is a noun. If it is a verb, you have to keep track of the tense. If it is a noun, the number. But also you need the semantic context. So if something is a capital of a state or anything that you can think of, right? All the information must be in this H0, Hn, but for the sake of the output, we may need to extract some part of this information, and we do this by linear projection. Now, I write down a little bit what happens and keep commenting on. So this Ki is a projection of the state. Why change the letters? I don't know. So I. So there is a key K vector related to any state in the encoder. Then I have Vi, that is another projection sorry, this should be V of the encoder. And then on this side I have the query, that is a suitable projection of the now decoder state. And the convention here is that, okay, you look at the previous one. So all these vectors are linear projection of states in the encoder or the decoder. And then we combine them basically as in this kind of single context thing. So we have the AI. Now I need a variable for, so probably I should use we first construct some kind of combination of the K and Q. That could be any kind of linear combination. And then we do the softmax thing to get the weights that combines, so that we have now a variable context, Ci, that is our weighted average, not of the state function, but of this okay, these are the VIs. Where is the VI coming from? No, this is W, yes. Yeah, of the projection of the state. And then we have the final outcome, that is the state, this is input, and the context for that particular point in the sequence. Okay, so what has happened here? So we have at some point in the decoding a projection of the state of the decoder that is basically here looking for something similar in the encoding, right? So this one you could think as a scalar product that combines the relevant information from the state of the decoder with the relevant information in the state of the encoder. So here we have a scalar product or some kind of linear projection of the query, the Q with the key. So this is similar to database search, in which we are looking for a key that matches our query. But then we need the information, and this is stored in the value, the V. So this is another projection that contains the meaning of what we are looking for in the form of another linear projection. And then we construct the context so that through this softmax is kind of highlighting part of the input value that are relevant for the output, and so that determines the output. So the state and well, okay, what I didn't write is that of course the state is always just a function of the state. So you always give the input because it gives the position where you are, but of the state, right? So this is what we get out, our translation. So that this is a kind of the most generic, well, not yet most generic, but a generic way to say, I want that in my sequence-to-sequence learning, I focus on different parts of the input, and this is learned, right? So all these are learned parameters. Everything here are just matrices, and each of these is a learned parameter. The advantage with respect to just try to put everything together is, of course, that then you kind of limit the size of these matrices instead of just having all possible part of the inputs that connect with all possible part of the output. The kind of difficult part to get the head around, at least it was for me, is that you think at any possible assignment of meaning to your sequence as some kind of rotation translation in the vector space in which you have embedded your sequence, right? So if it is language, each word has been embedded, and then they are combined together to make the sentence, and there is just one vector that is the sentence, and then you extract with this query mechanism the thing that it is most important in at that point. And as I was saying for the convolutional network, then you have to decouple from the intuitive understanding, like the filter is highlighting the edges or blurring the image because we are looking for just an average content. And here you focus on the grammatical part or the specific meaning of a word. Then you have to decouple that from what the actual is actually doing. So it is doing these kind of things, but not telling us, because we didn't train the network to tell us. Now we have all the field of trying to understand what the network is doing, but that's another story. But I like to think that the intuition when people started implementing this architecture was in this way, and this is relevant in the fact that they call it query key value, because they say, okay, there is something in my embedding that is related to the input. The moment I extract it, I assign any possible value, because that is also something that I learned. And then how more complicated this could be. So what I have sketched here is the, put it this way, yes, here. No, I don't like that. No. Like this. This is single head attention. So in this way, you would have for each kind of point in the output, you have one kind of V vector, value vector that comes from one query that you do on your input. Now you say, okay, but the very example that I just made, you may want to at the same time capture grammatics, semantics, and different level of semantics. If you have he in a sentence, it has to be connected to who was he in the previous sentence, if it was specified. So this has to be kept track of. So you may have different queries, and now should be then. I don't know if I copied just this one. Yes, let me copy this one. No, I need more space. So So now I have my H0, and then I would have key value and another key value. Now I have to be consistent with the indexing. So now there is another index. So that is 0, 0. And then I would have the same for H1 and so on. And then dot, 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 I start having state of the output. And I have now, one output, but now I have many possible query 1, 0, query 1, 1. So this would be the state 0. Oh, one thing I didn't specify, there is always a kind of state -1 with a Q0 and no output. So this is just the initialization of the sequence. These are all learnable. It's like a bias in your network. Now I have all this, and then now I just have an extra index. So I have that key depends so it's very similar with the previous step, but we just allow to have more of this key value, query key value triplets for each time step. V, H, I, and then on the other side you have the W, Q, S, I -1, use -1. Well, I need the other variable, T and T. And then I construct the intermediate weights by combining the K with the Q. Then I softmax, and I get the weights. And in general, so I get my weights, and then I get my context. And then I get my prediction. So the evolution of the state that depends on the input and this set of context variables. So now here what we did with this now multi-head attention is to just have the same story as explained above, except that now we have for each single instance multiple of these attention mechanisms, and so in this way we have not so we have all these parallel operations that are taken care of at the same time. So it is important that each of these KV is decoupled from each other. So each of them will adapt to look for something in your encoding, and decoding that is relevant. But we still have a kind of sequencing in the fact that we have to relate the keys at step 1 in the encoder to the key, so the state at the previous step, because we are still doing all the propagation. The multi-head attention is not yet the final great idea in order to get these sequence-to-sequence kind of models, because we would need to train the network by just waiting for the sequence of all the inputs to unfold. And the same when we have trained the network, we would need to give the input in sequence. So we need to wait that all the input is processed. So the next not the crucial, all this is crucial, but the final ingredient to get to transformers is the self-attention mechanism. Where we basically now move all the K, V, and Q to the encoder, so that we essentially decouple the evaluation of this transformation. I will not rewrite the whole thing. Is the same, but we just move everything to the encoder, and this makes our self-attention mechanism. So in practice, what we need, so what people have for a language model is, so we have our input, and then we have a multi-head self-attention layer that is basically evaluating these matrices in parallel over all the input, and then there is some kind of multi-layer perceptron before giving the output, right? So all this is combined in some kind of very large representation, and then we have a fully connected network. So this is, you have it everywhere, right? So even convolutional network, at the end of the convolution layers, there is you take whatever is the output of the convolution layers, linearize in one vector, and then you apply a multi-layer perceptron to the overall thing, because you want to give them the overall freedom to rearrange the map. And then okay, so then I want to basically, where did I have it? Oh, I lost my... So I had a sketch of the transformer somewhere. I lost it. Okay. Let me go back to that. Yep. So this is sketch from the original paper on transformers. That was basically also the architecture of the first GPT, and with not much difference also later generations of language models. So this should now be a bit understandable. So we go from inputs, sequence of words, to the input embedding. So we went through the one-hot encoding, and then we have the input embedding. Forget a bit of the positional encoding 1 second. And then this is given to this multi-head attention. Actually, it should be self-attention. And yeah, there is something that normalizes the output that doesn't really matter. So we have this multi-attention mechanism that I just explained, and then this goes feed-forward is another name for multi-layer perceptron. So this is another fully connected network. And this is repeated. So people said, okay, one of these modules is not enough, I do it over and over. So I repeat this thing in time. But you have multi-head attention, feed-forward, repeated over and over. The coder part, we have the same kind of repetition of things. The only difference is that initially when we give the output, so think of the translation, we have to mask it, meaning that we don't give the outputs beyond the first step for the coding. So the sequence doesn't know yet what happens afterwards, because otherwise the learning is polluted. So the learning already knows what's going to happen. So you have to give the sequence in kind of chunks that respect this kind of time sequences. And then you have at the end a final layer that makes the probabilities, right? So at the end you get probabilities, and then you have to softmax in order to select what actually you want to get as an output. So this is all that is there. This extra bit is that if you do self-attention, you destroy the sequence in the sequence, so you don't know what came first and what came later. So there is another part that keeps track of the sequence that actually turns out to be a Fourier transform, but it doesn't. I mean, it's just a technicality that people found. So you have to keep this information, but you store it separately. So all this part here are massively parallel. So you can give any long test for input, translation, captioning, summary, whatever you give as an output, and it will be trained. And all the training is doing is to tune these weights here, so that basically each of the attention mechanisms kind of specializes on some context and then combine it together in order to get the overall prediction. And the power of this is that, okay, it has been heavily developed for language, but there could be everything there. So we are getting a little bit probably too comfortable in just prompting. So having models where we prompt in natural languages to get the natural language output, but this kind of architecture it could be powerful in giving many different kind of representations from science, so from chemistry, material science, and get anything that is a meaningful output, right? So it could be a description, it could be a paper, a fully written paper, and but it could be just a sequence of numbers that we interpret as something, because that is what the network has been learning. And to give a kind of bookkeeping of the numbers here, so bookkeeping to get an idea on the size of this thing. I mean, you have heard about the overall size of the network, but just to see what is what keeping. So I found this for GPT-3. So we have the embedding part. So there is a dictionary of 50,000 tokens. So now, as they say, it's not necessarily words, but loosely connected to words in a dictionary, and it embeds into the exact number is 12,288 dimensions. So the one-hot encoding is projected into this 12,000 dimension representation for the both the input and the output. Then we have the query key and value matrices, and these are 128 times 12,288. So this, where do I have it? Yeah. So the 12,000 is the representation, same in the input and in the state vector. So the overall information is embedded in this 12,000 and something dimension state, and this is projected onto 128 dimension. So this is what I mean by saying each query key value is carrying a kind of confined part of the information, and strictly speaking is a linear manifold onto which we are projecting our thing. So, and then there are 96 of these heads, right? So this is here the L of the heads. So there are 96 for each input. So for the representation, you have 96 heads, and here, this thing is repeated 96 times as well. I don't know why they liked 96, but 96. So this gives a total of 15 billions parameters for the K part, and exactly the same for all the other ones. Well, right. And then we, yeah, okay. Yeah, I'm missing one. Okay, there is an output to this attention mechanism before we get the actual Y. So there is an output here. Output here. And this is also the same dimensionality, so there are another 15 giga. So all this together is 60 billions parameters, and then there are the multi-layer perceptrons, this part here, that overall give another 120. So for a total of 180 billions parameters that are distributed into these different part.
Small question.
Yeah.
So we have 50,000 different tokens that are in that network, or that can be learned, or no, that
can be represented.
represented.
Yeah.
And how can 50,000 be represented in only roughly 12,000 one-hot encoded dimensions?
So no, the one-hot is the 50,000. 50,000 is the one-hot encoding,
Okay.
and then is projected onto this.
So after the embedding.
Yes, and so and then there is the unembedding. What is it called? Yeah, I think unembedding.
Okay. Yeah. Then I understand.
Yeah, then we go. And here, these are also learned parameters. like 600 millions more or less, and then you have the unembedding. Well, it's the transpose of that matrix. Yes, that is actually very cheap, and this embedding is already something. So it is learned, and it is something can be used separately from the language model itself, right? So there are word embedding models, like the first and still quite famous is BERT. It is just something that goes from sentence to the embedding, and you can do geometry essentially. So the sentences that are embedded close by from the metric, they have similar content, so you can do some kind of other analysis other than the full powerful language model. So these are pre-trained, right? So you can I'm in one project I'm using that to kind of learn the similarities among scientific abstracts. So and we want to kind of do the clustering and see which abstract deal about some certain concept, and then this is related to content that we have in a database. But this is one of the many possible things. Final point for today is also related to your question. So there is a property of high-dimensional spaces. So high-dimensional spaces are highly non-intuitive. So you have these things that I mentioned at the very beginning of the course of dimensionality. Here we have a kind of sort of a feature that plays with us instead of against us, like in the course of dimensionality, that everything is distant from everything else. So if you ask, so if you have a space with n dimensions, by definition you have n independent directions. So you have a basis of n orthogonal vectors. But if you now give a little bit of leeway and you start asking about how many quasi-orthogonal directions there are, the answer is surprising. So if you do the experiment and you say, so we want to know number of quasi-orthogonal dimension in dimension, well, vectors, not dimensions. Dimensions do not change in dimension n. So if you actually do it to say I'm in 100 dimension, and I randomly extract 10,000 vectors, say okay with some constraint that the norm is 1, so unit vectors randomly. And you evaluate the scalar products. If you have a random, it could be even the Cartesian coordinates, and then you rescale it, and or you just work on the angles. Well, the Cartesian coordinate in n dimension is much easier. So you basically will end up in something that is so the most probable is 90 degrees. So you have a scalar product that it is, well, the scalar product would be 0. Probably it's better to do it like this. And if you also apply some kind of repulsion, so you take all the points and then you apply some kind of repulsive interaction between the two, you get easily something that it is even more picked in other dimensions. So that means that your random vectors will be distributed so that most of them are near orthogonal, and then you have a small kind of so the sigma of this Gaussian distribution is relatively it is small, and actually, so this would be kind of empirical. So we have a theorem, or to be more precise, it is a lemma of some more complex theorem. It's called the Johnson Lindenstrauss lemma that says that if you have n dimension, the number of pairs that you can construct that have a scalar product between minus epsilon and epsilon, so epsilon arbitrarily small, goes with the exponential of epsilon n. So as small as you take epsilon, with a large number of dimensions, the number of directions that you can have in that are almost orthogonal grows exponentially. So in these thousands of dimensions, we can hide many more almost orthogonal representations, right? So it would be all decoupled from each other. So you basically can encode this 12,000 dimension in GPT-3 is the overall playground. So it has to embed everything, and GPT-3 was already, I mean, nothing compared to GPT-5, but it was already astonishingly kind of accurate most of the time. So this is something very interesting when you go to this very large dimension, well, very large, still we are talking about thousands, not billions, representation, you can encode a lot of information. And this is a kind of, it is very powerful. Okay, I can stop here. Here.